The final section we are going to cover before we take our test is improper integrals. And an improper integral is a definite integral So remember, definite integrals are integrals where we do have bounds to plug in, but we're going to have problems with those bounds. So there's two things that we might see where the bounds might be infinite, so we might be trying to integrate all the way to infinity, or we could classify an integral as an improper integral if our function is going off to infinity somewhere on our interval. So either it's because the x value is infinity, or because the y value is infinity somewhere on the graph, if we were to look at this graph of the area that we were trying to calculate. So our improper integral is a definite integral where either the bounds are infinite or the function is infinite. On the given interval. And I'm going to show you pictures of both of them before we actually talk about how to do this. So when we have infinite bounds, they could either both be infinite or just one of them could be infinite. So we could be asked to integrate from 0 to infinity f of x dx, which means I keep wanting to go forever that way, and I'm trying to figure out the area. We could also go, say, negative infinity up to 2. So this one just has an infinite bound on the left. So let's say that's 2. So we could just have one side be infinite, or we could integrate from negative infinity to positive infinity and have both sides be infinite. And I want to know all of the area under this graph from negative infinity to positive infinity, which sometimes we can calculate and sometimes we can't. So with that in mind, let me tell you, if we can calculate this, and we do get a number, a real finite number answer back, then we say the integral is convergent. If for some reason we can't do this integral, and we would not be able to do it if there was, when we did our antiderivative and we tried to evaluate at infinity, if there were still infinities in the answer. So if there was an infinite amount of area under that graph. So otherwise, the integral is divergent. And this typically happens when we attempt to evaluate it and there are still infinities in our answer. We're actually going to be rewriting these integrals with limits, and we may get some limits that don't have answers to them. So those integrals would be divergent. So we're not getting a finite answer. Then they're divergent. So this is what it would look like if we were working with infinite bounds. So it could either be an infinite bound to the right or to the left, or in both directions. It's possible. It's also possible that it's not our interval that's infinite, but it's our function that's infinite. And that would happen because usually of an asymptote. A vertical asymptote. So these are a little bit harder to spot because the bounds would look perfectly fine. We might be integrating from 0 to 3. So it's really important to analyze that function and make sure you understand the function that you're working with. And we might be working with a function that has a vertical asymptote at 2. And then we're being asked to find the area from 1 to 3. But there in between 1 and 3, the function goes off to infinity. So that would also be an improper integral, because the function itself is infinite. So in this case, it's infinite in the center of our interval. Oh, I said 0 to 3, I'm sorry. Let me fix that. It's also possible just that one of our endpoints is infinite. So maybe with this exact same function, I said, what's the integral from 0 to 2 of f of x dx? So there's 2. And we're being asked to find all of this area. We're not asked about anything to the right of 2, but we wanted everything from 0 to 2. So it could be that the point where our function goes infinite is somewhere in the middle of our interval, or it could be that it's at the endpoints of one of the endpoints of our interval. And it's important to make the distinction between those two because we're going to deal with them a little bit differently. So the most important thing to understand, it doesn't matter whether we're dealing with infinities at our endpoints or whether we're dealing with real numbers at our endpoints, is that when you evaluate an integral, you always want to make sure that one of your endpoints is the function is defined and can be evaluated there. You don't want both of the endpoints to be infinite. So for 0 to 2, 0 is perfectly fine. This function has a value at 0. It's 2 that it's infinite. For negative infinity to positive infinity, both of them are infinite endpoints, so that would not be good. So when you evaluate an integral, you always want to make sure that any asymptotes within the interval are identified, and you have at least one good endpoint. So good is a very subjective word, but it means our function is defined. We're not going to have any trouble integrating and evaluating there. For those other endpoints, when we're going off to infinity or we're trying to evaluate at an asymptote, we're going to turn those into limits. And I'm going to call those our bad endpoints. We're going to turn our bad endpoints into limits. We can't exactly plug 2 into this function. What gives us vertical asymptotes are typically values that make 0 in the denominator. And we're not allowed to divide by 0. So that's why 2 is a vertical asymptote. So what we do instead is we just ask, well, what is the limit as x approaches 2 for this function? We're not actually going to plug 2 in, but we're going to look at the limit as it approaches 2. So we're going to turn all those bad endpoints into limits. And we're going to look at this in a couple of different cases. If your interval has no internal issues, so you look at the graph and you don't see any asymptotes. The only issue really is that one of your endpoints is an asymptote, or they're asking you to go off to infinity. So you've got positive or negative infinity or an endpoint asymptote. And let's also say here that you've got one good endpoint. So just as an example, I'm going to say like b to infinity. So b is a good endpoint. Infinity, that's a bad one. We can't plug infinity into a function, but we can figure out the limit as x approaches infinity. So we would find our antiderivative, which we call capital F. And typically we would evaluate at our endpoints. Since we can't actually plug infinity in, what we ask ourselves instead is, what is the limit as x approaches infinity for this function? But b is a good endpoint, so we can do minus f of b. So this is the piece where we'll have some work to do. And we're back to limits here, figuring out limits. So these bad endpoints that we're going to end up with, either because they're positive or negative infinity, or because we've got asymptotes in the middle or asymptotes at the end of our interval, we have to treat them as limits. So in this first case, there's no problems in the middle. We just have one bad endpoint. So either we have an asymptote at the end, or we've got an infinity, positive or negative infinity at the end. We can plug the good endpoint in just like normal, but that bad endpoint in we have to treat like a limit. If we do have an internal issue, so we've got good endpoints, and probably at first glance you're going to look at this problem and not think there's any issues with it at all until you look at your integrand and realize, ooh, my interval's 0 to 3 and I've got to asymptote it too. Yeah, there's going to be a problem inside my interval there. So good endpoints, but like an asymptote inside the interval. What we have to do is break apart our integral into two pieces. We have to analyze what's happening at that asymptote. So suppose f of x has a vertical asymptote at x equals c, where a is less than c is less than b. And we're asked to integrate from a to b, f of x dx. So a and b are perfectly fine numbers, and we can integrate f, and we can plug in a, and we can plug in b, and we can get an answer, and everything's going to look just fine. But you're going to miss something, because our function f goes infinite somewhere in between a and b, and that spot has got to be analyzed individually. So really what we have to do is we have to break up this integral, and we have to say a to c f of x dx plus c to b. I'm still covering my full interval a to c. I've just broken it apart at my bad spot because I have to analyze what exactly is happening at my bad spot. Now a and b are still perfectly fine to plug in. So both of my integrals have a good number to plug in, and then my c's are going to be treated like limits. So I'm only going to do one of these just as an example. So for this one, we would do our antiderivative, which is capital F, and then evaluate at c and a. But since c was a bad spot, we would really have to think of it as the limit as x approaches c for f of x. And then a was perfectly fine, so then we could just subtract f of a. And then this is where we might have a little bit of work to do to figure that out. And then we would do the exact same for this one, and then just add the two results together. The third case we might encounter is both the endpoints are bad. Now, it could be because they are both positive and negative, both infinity, or because they're both asymptotes. But either way, both endpoints are bad. We can't use either one of them. Neither one of them can be plugged back into that function to get a real finite value back. So just an example of this, if we were to ask to integrate from negative infinity to positive infinity, I technically can't plug either of those in to f. I can do both of their limits, but I can't plug either one of them in. So remember what I said earlier, every single integral has to have a good spot in it. So this one also, we're going to have to break it apart. And where you break it apart is completely up to you. Just make sure you break it apart at a value where f is defined. So I'm just going to pick some random a value, and I'm just going to make sure f is defined there, and I'm going to split my negative infinity to positive infinity interval up into two pieces, and I'm going to say, well, I'm going to do negative infinity to a, and then a to infinity. So I'm still covering the full interval, but we have to make sure that we analyze exactly what's happening at negative infinity and positive infinity, and our integrals have to have at least one good point in there. And then just like the last one, I'm just going to show you what to do with the first piece. It's going to end up just like the last one. We're going to get our antiderivative, capital F, and we're supposed to evaluate this at the upper and the lower. Now we can do f of a. Remember we said that was f was defined there, but we can't just plug negative infinity in. That has to be done as a limit. So then we would do the limit as x approaches negative infinity for f of x for the lower piece. And this is where most of the work is going to get done. And then we would do the exact same for this one and add our two results. So these are just definite integrals. The integration should be pretty straightforward. We've got values to plug in. The only different thing about definite integrals now is that we have these bad endpoints. And what's bad about them is either the endpoints themselves are infinities, or our function value is going to infinity, either at the endpoint or somewhere in our interval. So let's look at a couple of these. So the first one we're going to try is the integral from negative infinity to 0 for e to the 3x. The first thing you should always check is your integrand and make sure that it doesn't have any discontinuities, especially any vertical asymptotes. It's always good to type it into your graphing calculator or into Desmos really quick and see what it looks like. E to the 3x is a nice smooth continuous function. Its domain is negative infinity to positive infinity. No issues with it whatsoever. So the only problem here with this integral is the fact that we're being asked to evaluate the antiderivative at negative infinity. So that's what makes this thing improper. We don't have to deal with that quite yet. The first thing we need to do is find our antiderivative. So the antiderivative for e to the 3x is 1/3 e to the 3x. And then we plug in our top value. So 1/3 e to the 3 times 0 minus. We can't plug in the bottom value. You technically can't just plug in negative infinity. What we do instead is we ask ourselves, what is the limit as x approaches negative infinity for this function? And if you're not sure what that limit is, it's always good to look at the graph. We're technically asking ourselves, what is happening on the left side of the graph? X is approaching negative infinity far off on the left side of the graph. So take a look at the graph of 1/3 e to the 3x. It looks very similar to the e to the 3x graph, except it is compressed. It is squished down towards the x-axis a little bit more. So the first piece here, 1/3 e to the 3 times 0. Well, 3 times 0 is 0. E to the 0 power is 1. And then 1/3 times 1 is 1/3. And then this function, as x approaches negative infinity, it's approaching 0. The e graph has a horizontal asymptote of y equals 0 as x approaches negative infinity. So that piece is going to 0. So we get an answer of 1/3. So very often you can figure out these limits by taking a look at what's happening on that graph, especially when it's an infinite limit as x approaches positive or negative infinity. The next one, we want to know what the integral from 0 to 2 of 3 over x minus 1 squared is. Well, integral from 0 to 2, that doesn't seem like a problem. But then if you look at this function, 3 divided by x minus 1 squared, this function is going to have a vertical asymptote at x equals 1. And x equals 1 is in our interval. So that is a problem. So this is an improper integral. If you take a look at a graph of your integrand, it's got a vertical asymptote at 1. And then it swoops down from both sides. And we're being asked to find the area from 0 to 2. If that area is finite. It might be infinite. We don't know. We will see. First thing we have to do is break this thing apart. We have to be able to analyze that bad spot. And right now that bad spot is not sticking out in our integral. So I'm going to break this apart as an integral from 0 to 1 of 3 over x minus 1 squared, and then 1 to 2. So I'm still spanning my full 0 to 2 integral. I've just broken it up into 2 pieces. So they've got the same integrand. The integrands are going to have the exact same antiderivative. And just for some practice, for our antiderivative here, we can just do a u substitution. So if we let u equal x minus 1, du is going to equal 1 dx. And this turns into the integral of 3 over u squared du, or 3u to the negative 2 du. And we can just do the power rule on that. So we add 1 to our power and divide by our new power, ends up negative 3u to the negative 1, or negative 3 over u as our antiderivative. So we've got negative 3 over x minus 1 evaluated from 0 to 1. And then we've got negative 3 over x minus 1 evaluated from 1 to 2. Now when we do this evaluating, 1 is the bad spot. We're going to have to treat that one like a limit. So for my first one, I really need to do the limit as x approaches 1 for negative 3 over x minus 1. But I can plug in 0. 0 minus 1 is negative 1, so negative 3 divided by negative 1 is a regular old 3. And then for the second one, we can plug in 2. 2 minus 1 is 1. Negative 3 divided by 1 is negative 3. And then subtract what you get when you plug in the lower one, but the lower one was the bad spot, so we have to treat that one like a limit. So if you look at this limit, the limit as x approaches 1 for negative 3 over x minus 1. That is still infinite. This is still a problem. I still can't plug 1 in there. Usually when we do limits, we just try direct substitution. If you plug 1 in, you're still being asked to divide by 0. If you plug a value really close to 1, like 0.9 or 1.1, let's do 1.1 just for the sake of coming out positive. If you plug 1.1 in there, 1.1 minus 1 is 0.1, which is a tenth. So negative 3 divided by a tenth is negative 30. So plugging in something really close to 1 gets a really big answer. If we get even closer to 1, so like 1.01, the difference is going to be 100th, and then when we divide, we get negative 300. And then if we do it again, 1.001, we're going to get negative 3,000. So this thing is actually going to negative infinity. Well, it's going to go to positive infinity on one side, negative infinity on the other side. Because if we plug in 0.9, the result in the denominator will be negative infinity. So we can't do this limit. This limit is still undefined. X equals 1 is still an asymptote. Even after we do the antiderivative, it's still something we're not allowed to do. We still cannot do this. Which means this integral is divergent. We can't do it. Which might seem weird because we didn't have a problem with the first one. We did the first antiderivative and we were able to calculate our limit. There are some functions that once you do your antiderivative, the issue you were having with your bad spot goes away. Or, especially with positive and negative x values, the horizontal asymptote issues, far off to the left and far off to the right, those aren't as serious an issue as these vertical asymptotes. Those vertical asymptotes are much more serious. We absolutely cannot do those. So these vertical asymptotes, when we did our antiderivative, they did not go away. We still have x minus 1 in the denominator, and we could not do those limits. So because that problem did not go away once we did our antiderivative, we still cannot get a real finite number answer. And we said at the beginning of this section, when that happens, we would call that divergent.